Have you ever paused mid-roast at a backyard barbecue, staring at those dancing flames, and thought, what is this stuff really? Why does it even happen? Fire surrounds you. Think of the cozy crackle of a campfire on a cool evening, the romantic flicker of a candle during dinner, or the reliable whoosh of a gas burner kicking on in your kitchen. You rub two sticks together or flick a lighter, and suddenly there's this mesmerizing, destructive force. But here's the kicker. Fire isn't some ancient mystery or random accident of nature. Peel back the layers, and you uncover a breathtaking story that ties into the very fabric of our world, how tiny particles buzz and bond, how energy zips around like an invisible current, and how the blazing sun above us drives it all, even explaining the existence of the forests we hike through. This journey will flip your understanding of the everyday upside down, making you see flames as portals to the universe's secrets. If you're recraving more revelations that blend science with wonder and make complex ideas feel accessible and thrilling, do yourself a favor and subscribe to the channel right now. You won't want to miss what's coming next. Alright, let's ignite this exploration. Let's kick things off with something simple yet profound. A plain old piece of wood. Perhaps a dry log from a chopped down tree, just sitting quietly on the ground. It's not doing much of anything. Nearby, the air is filled with oxygen molecules, those invisible bits that make up about a fifth of what we breathe. These two, the wood and the oxygen, have been in close proximity for what could be hours, days, or even longer stretches of time. Maybe this log has been lying in your backyard for weeks, exposed to the open air, and yet absolutely nothing dramatic is occurring. No sudden bursts of heat, no glowing embers, no billowing smoke. It's all just still, peaceful. Even the wood remains solid and unchanged. The oxygen continues to float harmlessly around it. This equilibrium could persist indefinitely through rainstorms, sunny days, and freezing nights. It's a setup that's remarkably stable on the surface. But to truly grasp why fire bursts forth when it does, we need to zoom way in, down to the scale of atoms, the building blocks of everything around us. Inside that seemingly inert wood, there's a wealth of carbon atoms. Carbon is the star player here. The key ingredient that trees accumulate over their lifetimes to form bark, branches, and trunks. Now, oxygen atoms in the surrounding air have this innate attraction to carbon. It's like they're destined partners in a cosmic dance. When an oxygen atom gets close enough to a carbon atom, they don't just politely shake hands, they snap together with incredible force, forming a new molecule, typically carbon dioxide or something similar depending on the conditions. This union isn't neutral, it's exothermic, meaning it unleashes a tremendous amount of energy. That released energy is what we experience as the heat and light of fire. In scientific terms, this bonded state is more stable, sitting at a lower energy level than when the atoms are separate. Nature loves stability. Systems tend to gravitate toward lower energy configurations, like water flowing downhill. However, there's a crucial obstacle preventing this happy union from happening spontaneously. When oxygen approaches carbon, if it's not coming in with sufficient speed or closeness, there's a repulsive force that kicks in a kind of atomic standoff. The atoms might brush against each other, sense the potential for connection, but then rebound apart like two magnets flipped to their repelling sides. They don't realize, in a manner of speaking, how perfect they'd be together because they can't quite bridge that gap. This is the core tension at play. Carbon and oxygen are drawn to each other, yearning to combine and release that pent-up energy. But initiating the process requires overcoming a significant hurdle. Scientists call this the activation energy barrier. It's the extra push needed to get the reaction started. To make this clearer, let's use an analogy from everyday physics. Imagine a small ball at the base of a gentle hill with a deep, inviting pit or crater on the other side of the summit. The ball would love to roll into that pit. It's a lower, more stable position where it can rest without effort. But to get there, it has to climb up the hill first. If the ball is just nudged lightly, it might start up the slope, but then lose momentum and roll right back down to where it started. It needs a strong enough shove to crest the top, after which gravity takes over, pulling it down into the crater with accelerating speed. In this scenario, the hill represents the activation energy barrier. The ball is like our atoms. Without enough initial energy that shows they can't make it over the hump to the bonded energy-releasing state. Applying this to our wood and air example, the oxygen molecules are constantly in motion, zipping around due to the natural kinetic energy in gases. They're colliding with the surface of the wood where carbon atoms are exposed at an astonishing rate. We're talking millions of even billions even billions of these microscopic impacts every single second. Each collision is a potential opportunity for reaction. Oxygen hits carbon. They get tantalizingly close. But at room temperature, the atoms aren't moving with enough vigor. They bounce off, separate, and try again later. This relentless but fruitless bumping can continue for extended periods. That SYA stack of firewood in your garage does unsuddenly erupt in flames on a whim. A piece of timber could sit exposed to oxygen for decades, centuries, or theoretically even millennia without igniting. The desire for reaction is there, buried in the atomic affinities, but the barrier holds firm, maintaining the status quo. So, how do we flip the switch? How does fire actually begin? It all comes down to providing that initial boost to overcome the barrier. Enter heat from a match, a spark, a lightning strike, or any source that raises the temperature in a localized area. When you strike a match, the friction generates intense heat, which transfers to the wood. This heat energizes the atoms. It makes them vibrate more intensely, move faster, and collide with greater force. Suddenly, a few oxygen atoms have the oomph to scale that metaphorical hill. They get close enough to carbon, push past the repulsion, and snap. They bond. That single successful reaction releases a burst of energy, which doesn't just dissipate harmlessly. Instead, it radiates outward, jiggling nearby atoms, accelerating them too. This is where the real excitement builds. Those newly energized atoms now have what it takes to overcome their own barriers. They collide, bond, release more energy, which energizes even more atoms. It's a chain reaction, amplifying rapidly. Think of it as a snowball rolling down a mountain. It starts small but gathers mass and speed, becoming an avalanche. In atomic terms, it's exponential growth. One successful bonding event triggers two more, those two trigger four become eight, and so on. Within fractions of a second, what began as a tiny spark escalates to billions of atoms reacting simultaneously. This sudden surge is why fire doesn't creep in gradually. It explodes into being, transforming from nothing to a roaring blaze, almost instantaneously. It's a runaway feedback loop, a self-amplifying process that's both elegant and terrifying in its efficiency. Let's dwell on this chain reaction a bit more, because it's the heartbeat of what makes fire so captivating and dangerous. Once initiated, the process becomes self-sustaining. The energy released from each atomic snap provides the heat needed to propel the next set of atoms over the barrier. Heat begets more reactions, which beget more heat, and the cycle spirals outward. This is why fires can spread so voraciously from a single ember to engulfing an entire forest if conditions allow. The heat radiates to adjacent fuel sources, priming them for ignition, while fresh oxygen rushes in to feed the frenzy. It's a perfect storm of chemistry and physics, where the output fuels the input in a continuous loop. Now, what about that heat we're feeling? It's easy to think of heat as some kind of invisible fluid pouring out of the fire, like steam from a kettle. But that's an outdated notion from centuries ago, when scientists believed in something called caloric theory. In reality, heat is nothing more or less than motion at the atomic level. Every atom and molecule is in constant vibration, rotation, or translation jiggling, as some physicists poetically put it. The intensity of this jiggle determines temperature. Slow jiggle means cold, fast jiggle means hot. When our carbon-oxygen reactions release energy, that energy manifests as increased kinetic motion in the surrounding particles. They speed up, collide harder, and transfer that agitation to anything nearby, like your skin when you hold your hand close to the flames, or that cup of coffee you might warm over a campfire. The sensation of warmth is your nerves detecting this transferred atomic bustle. This brings us to a fundamental truth. Fire isn't a tangible substance. You can't scoop it into a jar or weigh it on a scale. It's not a matter in the way wood or water is. Fire is a process dynamic, ongoing event. It's the visible manifestation of rapid chemical reactions where atoms are rearranging themselves at breakneck speed, liberating stored energy as heat, light, and sometimes sound. The flames you see are glowing hot gases, superheated by the reactions, emitting light as excited electrons in the atoms jump between energy levels and then fall back, releasing photons in the process. It's a cascade of transformations, self-perpetuating until one of the key ingredients runs out. To emphasize how self-sustaining it is, consider what it takes to extinguish a fire. You have to interrupt that feedback loop. Fire relies on three essentials: fuel like the wood, oxygen from the air, and heat to keep the reactions going. This is the classic fire triangle taught in safety classes. Remove any one leg and the whole structure collapses. Pour water on it. The water absorbs heat, cooling things below the threshold where atoms can overcome the barrier plus. It can create steam that displaces oxygen. Smother it with a blanket or dirt. You're cutting off the oxygen supply, starving the reactions, or if you remove the fuel by separating burning pieces, there's nothing left to react. Without intervention, though, the loop chugs along, spreading and intensifying. As we ponder this, natural curiosity leads us backward. Why hasn't this wood ignited before now? And where did the wood come from in the first place? Let's trace it to its roots. The wood is the remnant of a tree, and the tree's primary building material is carbon. But here's a mind bender that carbon didn't originate from the soil, as many assume. It's a widespread misconception that plants pull their mass from the ground, like drawing nutrients up through roots to bulk up. People observe a tiny seed planted in dirt, watch it sprout and grow into a massive oak, and figure the earth must be the source of all that weight. After all, the tree is rooted there, right? But that's not accurate at all. In truth, trees assemble the vast majority of their substance from the air around them, specifically from carbon dioxide, that colorless, odorless gas that's a tiny but crucial part of our atmosphere. Through a process called photosynthesis, trees inhale CO2 via tiny pores in their leaves called stoma. They combine this with water absorbed from the soil, which itself originates from rainfall, evaporated from oceans and lakes, ultimately from the sky. Using energy from sunlight, they perform a remarkable feat, splitting the carbon dioxide molecule apart. The carbon is retained and incorporated into the tree's structure-forming cellulose, lignin, and other compounds that give wood its strength and density. The oxygen no longer needed is released back into the air as a byproduct. This is why forests are often called the lungs of the planet. They're constantly pumping out the oxygen we depend on. Sunlight is the powerhouse behind this. It's not just warmth or light, it's packets of energy, photons streaming from the sun at the speed of light. These photons strike chlorophyll, the green pigment in leaves that gives plants their color. Chlorophyll absorbs the energy, using it to drive chemical reactions that break the strong bonds in CO2 and H. It's like the sun is providing the muscle to push against nature's tendency toward disorder. In thermodynamics terms, life creates order complex structures from chaos, but it requires an external energy input to do so. Without the sun, none of this happens. Trees couldn't grow, and the cycle of life as we know it would grind to a halt. To drive this home with evidence, let's revisit a groundbreaking experiment from history. In the early 17th century, a Belgian physician and chemist named Jan Baptist van Helmont set out to solve the puzzle of plant growth. He was skeptical of the idea that soil provided the bulk, so he conducted a meticulous test. He dried 200 pounds of soil thoroughly, placed it in a large pot, and planted a 5-pound willow tree sapling in it. For the next 5 years, he watered the tree exclusively with rainwater or distilled water, nothing else added, no fertilizers or amendments. He covered the soil to prevent dust or debris from contaminating it. At the end of the experiment, he carefully removed the tree, dried and weighed the soil again, and measured the tree. The results were astonishing. The willow had grown to a whopping 169 pounds, a gain of 164 pounds. But the soil, it had lost only about 2 ounces, a negligible amount. Where on earth did all that extra mass come from? Clearly not the soil, as it remained virtually unchanged. Van Helmont concluded that the growth must come from the water, he added, since that's what he supplied in abundance. He was partially right. Water does contribute hydrogen and oxygen atoms, but he missed the bigger picture. Modern science shows that the lion's share of the mass is carbon extracted from atmospheric CO2. The experiment has been replicated and refined over the centuries, confirming that plants are master alchemists, transmuting thin air into solid matter with solar power. This revelation flips our intuition. Trees aren't emerging from the earth. They're materializing from the sky. The soil does play a role, providing essential minerals like nitrogen, phosphorus, potassium, and trace elements that act as catalysts or building blocks for proteins and enzymes. These minerals make up a small percentage, often just 1 to 5% of the dry weight. They're what remains as ash when you burn wood, that gray residue in your fireplace. That's the ground's contribution, but the combustible part, the hefty bulk that fuels the flames, is carbon from the air, woven with hydrogen and oxygen from water. Now, linking back to fire. When you toss that log into a hearth and light it, You're essentially undoing the tree's hard work. Photosynthesis separated carbon from oxygen, storing solar energy in the form of chemical bonds that hold those atoms apart against their will. Fire reverses this. Carbon eagerly recombines with oxygen, snapping back together and releasing the trapped energy in a glorious rush. The heat and light pouring out, that's sunlight from yesteryear photons, absorbed by leaves perhaps a decade or a century ago, now liberated all at once. A campfire isn't just burning wood. It's unleashing stored sunshine, recycling the sun's radiance in a visible, warming spectacle. Ponder this next time you're toasting marshmallows. Every flicker in the flames is an echo of solar rays that bathed the tree's canopy long ago. The energy cycle is poetic on to plant 2 wood to fire back to atmosphere, ready for the next tree to capture it anew. But why doesn't this release happen without provocation? If the atoms are so keen to reunite, why the need for a match? It's that activation barrier rearing its head again. At everyday temperatures, the atomic jiggle is too tame. Collisions occur, but they're lackluster, failing to breach the threshold. The system lingers in a metastable state stable enough to persist, but not the absolute lowest energy configuration. It's precarious, like a snowball balanced on a ledge. It could tumble with a gust, but until then, it stays put. Examples of metastable states abound in nature and technology. Gasoline in your car's tank sits calmly with air, but introduce a spark in the engine, and it combusts controllably to power your drive. Food in your pantry doesn't self-oxidize into ash. It waits for digestion or cooking. Even in your body, enzymes lower activation barriers to enable reactions at body temperature without scorching you from within. Without these barriers, the world would be a tinderbox of constant explosions and livable chaos. Shifting gears, let's explore the oxygen's backstory. It's not a primordial feature of Earth. Billions of years ago, our planet's atmosphere was a mix of carbon dioxide, methane, nitrogen, and water vapor with scant free oxygen. Life was anaerobic, thriving without it. Then, around 2.4 billion years ago, cyanobacteria, tiny photosynthetic microbes, they began harvesting sunlight to split CO2, hoarding carbon for growth, and expelling oxygen as waste. This great oxidation event flooded the air with O2, initially catastrophic. Oxygen was toxic to many early life forms, triggering mass extinctions. But evolution adapted. Some organisms harnessed oxygen's reactivity for efficient energy extraction, leading to aerobic respiration, the process powering complex life, including us. Today, plants and phytoplankton maintain oxygen levels at about 21%, all as byproduct. Without this, fire couldn't sustain. It's the oxidizer enabling combustion. This closes a grand loop. Sun powers plants to produce fuel, biomass, and oxygen. Fire consumes both, yielding CO2 and water for reuse. Animals fit into we ingest plant-derived carbon, oxidize it in cells for energy, exhaling CO2. Respiration mirrors fire. Same carbon plus oxygen gives CO2 energy equation. But enzymes facilitated at 98.6 degrees Fahrenheit, capturing energy in ATP for muscles and brains. You're a slow-burning engine, combusting food to live. To ground this dissect of flame's anatomy, burning wood converts chemical potential to kinetic energy. Bonds break endothermic. New ones form exothermic, netting release. Heat accelerates atoms. Light arises from excited electrons dropping orbits, emitting photons. Flame colors vary: orange from carbon soot, blue from complete combustion. Additives like sodium yellow or copper green create fireworks hues via unique electron jumps. Smoke. Hot, unreacted particles, carbon bits buoyed upward by density differences. Ash, inorganics from soil. Mass consumed. What's not visible becomes gaseous CO2 and H2O. Fire's broader implications are vast. Ecologically, it renews landscapes. Clearing debris for new growth-prescribed burns mimic this. Human history pivots on fire. Mastering it enabled cooking, boosting nutrition, and brain size. Smelting metals sparked technology. Steam engines ignited industry. Yet, its dual-edged wildfires devastate, but teach resilience. Extending outward, fire analogs exist cosmically. Stars on nuclear fires, fusing hydrogen under gravity's crush, radiating energy that seeds life. Our suns jiggle its heat stems from fusion A tale for another day. We've traversed from atomic snaps to stellar scales, unveiling fire's essence. If this blazed a trail in your mind, hit like, comment your favorite insider suggestion for future topics, and subscribe to fuel more explorations. What's next on your curiosity list? Tell me below.